Yes, so I have started recording. So if you wish, you can give your attendances now. All right. So any questions from the previous class? All right. Then we will continue with our discussion on canonical transformations. So just to remind you that if we uh, did a transformation of the form, so suppose Qj equals uh, Qk Pk and Pj equals Pj Qk Pk. Then we defined column vectors x and y. So x contained uh, this Qi Pi, and y contained my new coordinates. It was capital Qi, capital Pi. In that case, I defined the element of something called a Jacobian matrix. So the jkth element would be given by del yj del xk. And for this transformation to be canonical, we needed to check that this Jacobian is symplectic, which was given by j gamma j transpose equals gamma, where this gamma is a matrix of this structure. All right. So this is the condition for canonical transformation. So this is my condition for canonical transformation. Great. Now we can get some idea or some insights into the physical reality by moving to the infinitesimal version of such transformations. So those transformations I will call by the name of infinitesimal canonical transformation, ICT in short. So first thing is that, so first my coordinate, let's say it changes to q, and this differs from the old coordinate by an infinitesimal amount, epsilon times fqp, okay, where epsilon tends to 0. Okay, so epsilon is a small quantity. So I am just uh, changing my coordinate and momenta, or my phase space coordinate rather, by an infinitesimal amount, which is parameterized by this epsilon, and I write it as this. Great. Now I ask, what is the condition uh, such that this transformation is canonical? So what is the condition on this f and g such that this infinitesimal transformation is canonical? Okay. So first, I know that I have to form the Jacobian for this. So for this, I will first construct my x and y things. So x is just qp, and y rather is just, okay. So now if I form the matrix J, so J will be given by, remember, so J11, according to my definition, this would be del x1 del, sorry, not del x1, this is del y1 by del x1, and this is essentially y1 is q and x1 is small q. So this is essentially del of capital Q over del small q. Similarly, this is 1, 2, so this should be del of capital Q over del of small p, and this should be del of, I guess, capital P over del of small q, and then del p, del p. This is my j. Okay, so I need to find these things. So now if I look at these expressions, this and this, so del q, so this quantity is just given by 1 plus epsilon del f del q. Then this quantity just epsilon times del f del p. Okay. Then let me put another color. Then this quantity del p is 1 plus epsilon del g del p, and then the last one is here, and this is epsilon del g del q. Okay. So for this transformation to be canonical, what I need to check is that my j transpose gamma j equals gamma. So I need to check this, sorry, j gamma j transpose, which to the first order of epsilon, if you expand, so you collect all these things, and then you can check that this should come out to be, I am writing from what I have calculated. So 1 uh, plus epsilon del f del q plus del g del p, and then minus 1 minus epsilon times del f del q plus del g del p again, and then here 0, plus terms of order epsilon square, which I will ignore because epsilon is so small. I assume that I can safely ignore terms of order epsilon square. All right. So I have to identify this as gamma. Okay. So this should be a gamma if the quantity is inside this first bracket is 0. Okay, so you can check, then the matrix reduces to 0, 1 minus 1 0, and if the quantity inside my first bracket is 0, then this is my gamma. All right. So for that quantity to be 0, I get one very simple relation. Okay, so the relation, so condition for, let's say, ICT, infinitesimal canonical transformation, is del f over del q equals minus del g over del p. Right. Now, this will be true if f and g can be written as, perhaps you have seen this type of conditions before. Okay? These are the condition for something total in the context of total differential. You have seen this type of condition. So suppose if um, my g is a function of q and p, this capital G is a function of q and p, then you can write dg equals, how do you write it? Del g del q dq plus, not, so del g del q dq plus del g del p dp. Okay. So if I suppose if I had written it as, let's say, so I call it a minus G dq, and this one I will call f dp. Okay, so there's a plus sign. Now, if this is true, then for this to be a total differential, what do you check? You precisely check this condition. So if here G becomes minus del G del Q, so for G equals a function of Q and P, uh, small g is just minus del G del Q, and F is just del G del P. So for this condition to be satisfied, so if this is true, then you can check that the condition above is automatically satisfied, because both of them would be just del 2g del q del p. Okay, so if g is a function with all order of continuous derivatives, then this is obviously true, and you can say that f and g satisfies this condition. So remember, for f and g to for f and g to correspond to an infinitesimal canonical transformation of these forms, these ones, I see that this g and f should be generated from a single function. This is gqp. Okay. And if g and f are related via these relations to a single function, that is gqp, then I know that a transformation of this form, an infinitesimal transformation, an infinitesimal translation of an infinitesimal transformation of this form is basically a canonical transformation. Good. And this G would very often will be called the generator for that canonical transformation. So this will call be the generator for the canonical transformation, or infinitesimal canonical transformation. I mean, if you build on over it, then it would be the total canonical transformation. Is not a that is no surprise. Now, remember, there would be another term called the generating function, which we will talk about later. And do not confuse the generator with generating function as of yet. Okay, so generator is a different thing, and generating function would be discussed later. So this G generates, this capital G generates the canonical transformation in hand. Now, I don't know if you have noted this term generator in your either your quantum mechanics course or your mathematical methods course. Did the discussion on group theory started in mathematical methods course? Maybe continuous group generators. Did you hear?
Yes, sir. Yes, sir. Today only sir was teaching this generator.
Okay, okay. So in the context of continuous group, perhaps you have
Yes, sir. Lie group. Yes, sir.
yeah, Lie group. You have studied this. In quantum mechanics, did you also study that the momentum generates the translation along a certain direction? Did you learn that? I do not know. So if you, I do not know, in the Sakurai's book, perhaps you would have seen something like this. It's e to the power IPA, perhaps over h cross, if you do not put, and it operates on x, and it gives you x plus a. So it transforms the ket by a translation. Have you studied this kind of relation? No. Okay. Anyway, so you have not heard that momentum generates translation. Momentum is the generator of the translation. If you have not heard that in quantum mechanics, so this is the time to learn it in classical mechanics. How do we understand that? Okay. So to understand that, let me first write down the n-dimensional version of this transformation equation. Okay. So I can write my kth coordinate. Say qk goes to capital Qk, which is equals to small qk plus uh, epsilon times fk qp. Okay, and pk goes to capital Pk, which is equals small pk plus epsilon times gk on is a function of qp. Then again, for these transformations to be canonical, you need to have in the same spirit as these. So here you will have basically fk equals del g qp over del pk, and gk is equals minus del g del qk, function of q and p, of course. So this is the relations you have, right? Now, so this GQP, when I found out the condition for canonical transformation, I did not specify anything about this generator GQP. It could be any arbitrary function. So you take any arbitrary GQP, you get a canonical transformation. Now, not all the transformation would be of physical interest. If you take some particular choices for this GQP, you get some interesting aspect of symmetry that can really give you a better understanding of what's going on behind the curtain. Okay, so for example, just for fun, let me take GQP equals PK. Okay, so this is a spatial choice. This is a spatial choice, of course, where I just say that my GQP is just the momentum along the kth direction. So this is just the momentum along kth direction. Okay. If it is true, then from this relation, Fk equals del G del Pk. So let me not write it Pk. Let me write just Pi, or let's call it ith direction, because I have been taking derivative in this. Then my Fk will just be delta Ki, okay, and Gk will be 0, right? So if you take the derivative with respect to this Pk, like del Pi del Pk is delta Ki, and this is equal to 0. Now if you substitute these values in here, then what you get? You get capital Qk equals Qk plus epsilon delta Ki, and Pk equals to just Pk. So you notice uh, that is, so this represents just translation in the ith direction. Okay, so for k equals I, Qi is basically Qi plus epsilon. Okay, and everything else remains where they were. So this is just a translation in the ith direction. So that means, so this transformation, the resulting transformation that you got, is just a translation in the ith direction. Okay, that's it, nothing else. Okay, and what does generate translation in the ith direction? So this is your Pi. Okay, so if you take the generator to be your momentum in the ith direction, then you get a translation of coordinates in the ith direction, right? So the quantum mechanical version for this thing is this e to the power I p a over h. I mean, if you use h cross equals 1, then the infinitesimal version, so you call it, rather, let's say it is I p epsilon over h. So epsilon, if epsilon tends to 0, then this is basically 1 plus uh, I p epsilon over h cross operating on x. Okay, so that's it. So something like this. Okay, so now you compare this with so this means this is x plus I p epsilon over h cross on x. Okay, so you compare it with this thing, so qk is kind of x, it was originally in there, the epsilon parameter is also there, the h cross and I comes from quantum mechanics because you are changing Poisson bracket to, so I will come to that later, and fk is equals p, fk is equals basically p, so that's why the p is there, and it is operating, since these things are operator, it is operating on the coordinate vector. Okay, so the it is basically the same as this thing. So this is the kind of the quantum mechanical analog of the statement that a momentum generates a translation in the coordinate space. Okay, so that is why we make this statement that momentum is the generator of translation. I put translation and momentum under quote because if my momentum is my linear momentum, then the translation is a linear transformation. It's a linear translation because this qk is just like x, as I said. But if it is an angular momentum, then the corresponding coordinate is like the theta, the angular coordinate, and then a translation in the angular coordinate is equivalent to a rotation. Okay, so that is also a translation in an angular sense. So this statement is quite general, it means both. So if you talk about linear momentum, it generates translation, it generates translation, it generates linear translation, and if it is an angular momentum, it generates rotation. Okay, so this will also follow from group theory. If you are, I mean, just go through the book of Arfken. I think it is explained quite nicely there, and there are many way of looking into things. So in a way of classical mechanics, we can express it the way I talked about here. Okay, so I guess it's a good time to pause and check if there are questions. Any questions? Okay, so maybe I should ask, I mean, do you face any problem following these lectures? Because from the past few lectures, I am noticing that you are becoming increasingly silent. Is the pace all right, or I am going too fast? You can tell me that if you feel that it is going too fast.
Sir, actually, just it's sometimes that I personally like feel like the mathematics for this is easy, but to relate it like to the other aspects like the quantum you told us, so it sometimes becomes like kind of difficult. So
So yeah, you can just talk about that. I mean, I would suggest you also form an internal group among yourselves. I mean, I think you have already done that, and discuss the lectures internally within yourself. But if you have difficulty following the kind of sometimes the physics aspects I talk about, because to me those are more interesting things. I mean, the mathematics is trivial, as you can see, it's just derivatives. But the implications that you need to understand and you need to generalize and apply elsewhere, because in more advanced topics you are interested in, you should make the understanding very clear. Otherwise, you will face problem if you try to do theoretical physics at least. So if you have problems understanding what I am talking about, then tell me now. I mean, you can tell me, however trivial that is.
It's not like difficult. It's like when I watch it, and when I watch the recorded video, then I understand everything.
Oh, okay. Okay. If this is the general consensus among yourselves, then it's fine. I mean, if you watch the recorded video and if you understand, then it's fine then. All right, then I will carry on as I was. Okay. Anyone else has other comments? Okay, then. Good. So now let me move on. So there is another interesting interpretation of this, another interesting way of looking at canonical transformation. Okay. So the way I expressed those transformation, so basically I defined, in this case, let's say, let me do it again, qk equals qk plus epsilon fk qp, and pk equals small pk plus epsilon gk qp. Okay. So apparently this uh, the way I am writing it, I am parameterizing the canonical transformation using a parameter epsilon. Okay, so I introduce parameter epsilon. So basically, qk goes to another function qk, which is the function of the old coordinate, that is true, and parameterized by epsilon. Okay, and similarly, pk goes to pk, and it is parameterized by epsilon. And in the limit, so in the limit epsilon tends to 0, I get basically qk equals qk, and pk equals pk. So that I do not transform anything. There is no transformation in the limit epsilon tends to 0. Uh, so so that is the thing. Sorry, let me put epsilon equals to 0. So that is the thing. So in one way of looking at this is that you are this canonical transformation might mean that you are writing the same point, you are looking at the same phase space point, but in, say, different coordinate system. You are expressing the same point in a different coordinate system. Okay. So this is usually called a passive sense of looking at things. So suppose you have here q and p, and this was my phase space point that you called qp. So this coordinate transformation, usually you can interpret it as you are looking at the same point, but you are giving it a different name. Okay, just like you do with from Cartesian to spherical polar and to cylindrical polar coordinate. Okay. And but there is so there is another way of looking at it. It can give you an active sense of looking at things. So what I mean by that is that, so as I told you that this qk pk, this coordinate is equivalent to qk qp at epsilon equals 0 and pk qp at epsilon equals 0. Okay, so you can think about it that this epsilon is a parameter. You are looking at the evolution of the coordinate points with respect to parameter epsilon. If epsilon is a time, then that is time evolution. But in general, if epsilon is an arbitrary parameter that at this moment I do not know the physical meaning of, then this uh, this way of writing my transformation is something like writing the epsilon evolution of my coordinate qk and pk, and you can think about my small qk and small pk as the initial coordinates that was at epsilon equals to 0. So think about, think about with time, it basically is the same. Okay, so you can in the special case at epsilon is your time, then this qk pk is basically qk qp at t equals 0 and pk qp at t equals 0. Okay, so this makes the interpretation much straightforward, right? So if epsilon happens to be time, then this type of transformation gives me the time evolution. But if at this moment I do not know the physical interpretation of epsilon, then it's just an epsilon evolution. I do not know the physical meaning yet. Okay, now so there is another way of writing this. So I am trying to make this connection intentionally because I have something in mind. So if you notice at this infinitesimal transformation, if epsilon tells me the infinitesimal amount of transformation, the infinitesimal amount of parameter, then you can compare it with your Taylor expansion of small qk. So capital Qk is the change in small qk with parameter epsilon. So you can parameterize that. If you believe in Taylor series, then qk plus dqk d epsilon times epsilon. Okay, so that would be my Taylor expansion plus order epsilon square. Okay. If I compare this, and similarly this would be pk pk plus dpk d epsilon time epsilon plus order epsilon square. Okay. So comparing those two things, I basically have, if I treat epsilon as a parameter and I treat my canonical transformation to be an active evolution with parameter epsilon, and in a special case epsilon may become my time, then what I have is that this fk qp is basically equals dqk d epsilon. So you are basically comparing this with this, right? These two are the same thing. But I know from the and let me write down the another thing. So this gk qp is equals dpk d epsilon, and this equals to, according to my condition of canonical transformation, this dqk d epsilon should be minus del g, no, plus, this one is plus. So this is del g del pk, this is a function of q and p, and this is equals minus del g function of q and p by del qk. Great. So this is the equation that I got. Now notice this equation carefully. Okay. So So this gives you an amazing idea of what Hamilton's equations actually are. So these pair of equation looks exactly like your Hamilton's equation. If you replace epsilon by time, then this is just your Hamilton's equation, right? If you just think that there is time in the place of epsilon, then this is just your Hamilton's equation. So kind of the Hamilton's equation apparently is a special case of this kind of canonical equations. So these are these kind of equations I will call canonical equations in general, because this G is a generator of the canonical transformation, and this essentially enables me to interpret that the epsilon evolution of my coordinates in phase space will be governed by these kind of pairs of equation, which I will call canonical equations. And that's why Hamilton's equation is sometimes said to be a special kind of canonical equations. Okay, so when epsilon is equal to time. Okay, so so if epsilon is equivalent to t, then you get Hamilton's equation, and then this GQP is identified with your Hamiltonian operator, right? So your Hamiltonian is a special case of this kind of canonical transformation generator. So any arbitrary GQP would give you evolution along epsilon direction, will give you an epsilon evolution. Hamiltonian is a generator, is a special kind of generator which generates the evolution along time. Okay, so the Hamiltonian basically gives you the evolution along time. Okay, so this is one interpretation. So basically, Hamiltonians actually give you the time evolution of your system. Okay, so when epsilon is identified with time, then this Hamiltonian is your generator, and that's why it is called sometimes called the Hamiltonian generates the translation along time. Okay, so what you have here in this case, so for example, in the same way, see when pk, when you choose the linear momentum as your generator, when you choose sorry, not this one, sorry, pi as your generator, when you identify gqp as your pi, okay, then what you had is that you got your translation along the ith direction. So your canonical transformation became the translation along the ith direction, or the space translation, the space evolution of that thing. So if you identify your generator with a linear momentum or any kind of momentum, you get translation in certain sense. And if you identify the epsilon with time, then you get the generator. Sorry, in the other way, if you say that my generator is my Hamiltonian, okay, if G is your H, then you get time translation, or time evolution mean time translation. And that's why when you talk about the time evolution of states in quantum mechanics, you the time evolution operator U is equals you use it as IHT over H cross. I will remove this H cross. I don't like writing H cross everywhere. So it is IHT. Actually, you have so basically psi at t would be given by e to the power IHT. If you from t equals to 0 to at time t, the thing that basically governs the time evolution is your Hamiltonian. Okay, so and that's why you write your time evolution operator in quantum mechanics like this. And if you are not familiar, for stationary state, you have definitely seen that the time evolution operator might be a minus sign, e to the power minus e and t on psi 0. Perhaps you have seen this for stationary states at least. So now you have I hope you have a better grasp of why we do that, okay, or why it works actually. So from an classical analog, this is where it comes from. So this H is basically the generator of time evolution, and that's why. Okay, so perhaps you are noting a thing, a kind of a consistent pattern in here. So someone told me that you have started Lie groups in your mathematical methods course. So basically the group element of a Lie group, if I denote it by U, is basically given by e to the power I Ta times theta a. These theta a are your parameters of group transformation, and these TAs are called the generators of those transformation. Okay, so at least you have seen this, right? Can everyone tell me that this you have seen at least?
Yes, sir.
Yes, sir.
Good. So this theta a is your parameter of group transformation. Okay, this is your parameter, and this is your generator, right? Okay. And so in the infinitesimal form, you write it as e to the power I Ta theta a, and from this infinitesimal form, you basically find your Lie algebra Ta Tb equals I FABC TC. Okay, so this you find using the these things. But notice this thing. So the group transformation parameter is accompanied by the generator. Okay, so here is my transformation parameter T, and here is my generator H. Okay, so basically the same token. So that's why I call my H to be the generator of my time parameter. In the same token, by the same token, if you look at this one, this is my parameter, and so this is my generator. This is my translation parameter. This is my generator. These are all U1 groups. If you care about the name, okay. So so now you have perhaps make a deeper connection between the generators and the transformation that we are talking about. And so from this canonical transformation, you also get those connections. And you usually find in quantum mechanics that these canonically conjugate quantity. So here T and H are canonically conjugate quantities because one generates the translation in another direction. And here also P and epsilon, or rather P and X, are canonically conjugate quantities. And these canonically conjugate quantities have uncertainty relation. So in the case of delta P, delta Q, or greater than H cross, and you can also write down delta H, delta T greater than equals H cross. Okay, so this so that is basically another way of looking at so why Hamiltonian is connected to your time coordinate, because Hamiltonian can be in some way thought of as the generator of translation in the time direction, and that's why in this sense Hamiltonian and time are related, okay, in a canonically conjugate variables, and that's why you sort of expect this kind of uncertainty relation. By the way, in quantum mechanics, the source of this and source of this are probably different, but at least you get uncertainty relation in both these things. Okay, so let me tell you one more thing here, the thing that we are doing. So when we talk about this T and H here, and we talk about P and Q here, okay, P and Q here, we see that they are very similar in the sense of canonical transformation, but the way we treat them here in classical mechanics are very different. Here q and p are like coordinates, say phase space coordinates, and time t is a parameter. Okay? We take derivative with respect to total derivative with respect to t. We take time as an evolution parameter. So that is the that is inherent in my this formulation of classical mechanics. It is inherent that I am treating space and time differently. I'm treating space as real coordinates, which varies with time as a parameter. So I'm treating time as a parameter, but space as like physical coordinates. So this asymmetric nature of treating space and time makes our treatment inherently non-relativistic. Okay, so the relativistic formulation, if I do it in this class, will be the classical field theory, where we treat space and time in a symmetric footing, and we will see how it pans out there. Okay, so for now, it should to some degree satisfy you that you understand somehow that what is meant by canonically conjugate pairs of variables. Okay, so I will pause for a brief moment again and check if there are questions up until this point.
Sir,
Yes.
sir, can we in general say that Hamiltonian is a generator of time, or for special case like when we choose Hamiltonian equals to P, like we have chosen capital G equals to P?
No, capital G is the generator. In general, capital G is the generator of any canonical transformation. When you choose G equals P, it gives you space translation. When you choose G equals H, you get kind of time translation. That's what I mean.
No, sir, we have chosen capital G equals to small pi, then only we got that translation in the ith direction in the space coordinate. Similarly, if we take, instead of capital G, we take capital H and we choose it to be pi, then only we get time translation in general, or it is a special case. That's
No. You do not have to choose H to be anything. H is your Hamiltonian. So definition of H is such that, so the definition of H is something that gives me this relation. Okay. Q dot equals del H del P. Okay. So this is my definition of H. So H is a function which is related to P dot and Q dot are like this. Okay. And I do not know what is H, but whatever be the H, whatever be the H, you can interpret it as when my generator of the canonical transformation G is identified with H, then by virtue of these relations, since this already holds, I can identify in the same way that this G can be treated as the epsilon evolution, the generator of the epsilon evolution. This H can be thought of the generator of the time evolution, because these are basically dp dt. Okay, so when you treat t to be epsilon, doesn't matter. I mean, you don't have to choose H to be anything. H is something that is a function of Q and P, which is related to the like P dot and Q dot, like this one. I mean, even the H for a harmonic oscillator is still the generator for time translation. I mean, you don't have to choose H to be P or H to be anything. H is as general as it can be.
Okay, sir.
Okay.
So,
Yes.
so if we define capital G as a function of like Q, P, and time itself, so how will this particular epsilon?
This that will become obviously complicated, and there would be no straightforward implication for that. Like, you cannot connect to physics with that. Okay. And that's why we only talk about restricted canonical transformation.
Okay, sir. And so this epsilon, which like along which the evolution is going on, we chose it to be like T and got Hamiltonian for this choice, right? If you choose, we get
Yes,
epsilon.
yes, it's a special case. I mean, the for a general epsilon, if I do not know the physical meaning, it's a parameter. That is the general evolution. These are the general evolution. The Hamilton's equation are the special case with epsilon equals time.
Okay, sir.
Okay.
Sir, in Hamiltonian formalism, Q and P are independent coordinates.
Q and P are, yes, independent coordinates. I mean, it depends on what you mean by independent, in a sense that they both evolve with time, but we treat it as explicitly independent parameter. But my answer will depend on what you ask next.
Suppose H is equal to the energy E, then they are dependent. We can relate,
Yes.
we can
Yes.
construct a phase
Yes.
space. But if
Yes.
H is not, H is a function of time, then they are independent.
Well, then energy is not conserved, but you do not know if anything else is conserved, and that relates with Q and P. I mean, see, H gives you the time evolution of Q and P, right? I mean, if you give me the initial condition, I can find Q equals QT and P equals PT. Okay.
Yes.
These are both dependent. So give one point of time, you give one value of T, and I know both Q and P. Okay, if the initial conditions are known, then, well, in the same way, you say that Q and P can be fixed if I know one. It can be fixed also if you specify T here.
Okay.
It doesn't matter whether your Hamiltonian depends on T or not.
Okay.
Okay. The point is that if you are considering the time evolution of a system in one dimension, so the one dimension time evolution of a system is a second order differential equation as given by the Euler-Lagrange equation. So if you give me two boundary conditions, let's say the position of the particle or the position of the system and the momentum of the system at t equals 0, in principle, I can solve the second order differential equation to find out Q and P explicitly like this. And by virtue that this is a one-dimensional problem, if I know Q at one instant of time, I also know P. That's it.
Okay.
Anything else? All right. So before I close today's session, let me talk about something very quickly. Don't worry if you do not get this part, I will come to that again. Okay. So again, I will talk about systems where Hamiltonian do not explicitly depend on time. Okay. So suppose again I write down my qk is equals qk plus epsilon fk, and pk is equals small pk plus epsilon gk. Okay. Now from this, you know the infinitesimal change in q coordinate, so which I denote by delta qk, which I will write as qk minus small qk. This is equals epsilon fk, which is again del g del pk, I guess. And similarly, you can write delta pk, which is equals pk minus qk, which is equals to minus epsilon times del g del qk. Okay. So if you change your qk and pk like this, then your Hamiltonian, which was a function of again q and p, will in general also change. So delta h would be given by summation over k del h del qk times delta qk plus del h del pk delta pk. Now I can plug in my delta qk and delta pk from here, and if I do that, this basically turns out to be this del h del qk and del g del pk minus del h del pk dot del g del qk. Here you can readily see the point with quantum mechanics. So this has like immensely important implications. So now you can see where I am going here. So these kind of things, this kind of I would encounter very often uh, in classical mechanics afterwards. So I like introduce a shorthand for this summation. I call it the Poisson bracket between h and g, and this delta h is basically equals to epsilon times the Poisson bracket of h and g, right? Now again, if nothing happens to the Hamiltonian if you make this transformation, if this transformation with parameter epsilon is a symmetry of the Hamiltonian or the symmetry of the system, then you know that the symmetry, that this delta H will be zero, the change in Hamiltonian will be zero if that is a symmetry operation. So if this is a symmetry operation, like both of these actually, so together these constitute a symmetry operation, by which I mean that if that is a symmetry operation of your thing, then the Poisson bracket with the generator of the Hamiltonian, sorry, the Poisson bracket of the Hamiltonian with the generator is 0. So this Hg is equals to 0 if the generator generates a symmetry of uh, uh, the Hamiltonian. Okay, so for now you might be like you might totally in dark what this has to do with other things. So before you come tomorrow in the next class, I want you to think about these things. What are the implications that you can think about? Okay, where did you find this kind of relation? So this is the statement, the equivalent statement in quantum mechanics is that if there is a symmetry, then you know there is a conserved quantity, and now you see that there is also a Poisson bracket, or the Poisson bracket between the Hamiltonian and the corresponding generator of that coordinate transformation is also 0. Now you can perhaps guess that these Poisson bracket things would be related to commutators in quantum mechanics, and the equivalent statement will be whenever there is a symmetry of the Hamiltonian, then the corresponding generator should commute with the Hamiltonian. It will always happen. Okay, so suppose you take the idea of a free particle in one dimension. What is the Hamiltonian in quantum mechanics? Is p square over 2m. Okay, so if you think about the thing like this translation, so if a free particle is in one dimension, then I told you that there is a translational symmetry. It doesn't matter where you choose your origin to be. So for a free particle, there is a translational symmetry, and I know the generator for the translational symmetry, the G for translational symmetry is your momentum, that is P. Okay, and that's why you can write that H commutator P is equals to 0 for a free particle. Okay, for a free particle in one dimension, and you can get that. Okay, so think about other examples if you can figure out things like that from here. Okay, so this is a restatement of Noether's theorem in classical mechanics, that if there is a symmetry, that you change your coordinates in a certain way, and your G generates that coordinate transformation, then the Hamiltonian should commute with the corresponding generator of the transformation. And in a special case when you have a free particle in one dimension, there is a translational symmetry, and by now you know that momentum generates your translation, and that's why Hamiltonian commutes with momentum. You do not need to do any explicit calculation. So you can guess things, you can see things through before doing any calculation if you have ideas like this. Okay? If you understand what these things mean, then yeah. So with this, I will stop today's lecture here, and tell me if you have any quick questions.
So, like for momentum, you said that there is a translational symmetry, so so the result was like 0. But if you like take the Hamiltonian with Hamiltonian, so what kind of like can we say that symmetry? Time symmetry, I mean. So.
Yes, that basically means that your Schrodinger equation. I mean, it doesn't matter when you start your clock.
Oh, okay.
I mean, it is always true. There's a time symmetry in there.
Okay, sir. Thank you, sir.
Okay. It doesn't matter when you take your t equals to 0. The description of your physical system doesn't depend when you start your clock. So that's why Hamiltonian always commutes with the Hamiltonian, in a sense.
Excuse me, sir.
Okay, sir.
Yes.
Sir, you said earlier that the generator is means we can choose any generator, but here we find a bound on generator with its Poisson bracket with the Hamiltonian to be 0. So we can only have special generators. Is this the case?
See, an arbitrary generator will generate arbitrary transformations. So Fk and Gk would be arbitrary. Now for some special Fk and Gk, this del H will be 0. Okay, so those are my symmetry transformations. So those are my good generators, which generates a symmetry transformation. So my Hamiltonian only Poisson commutes with those generators, not any arbitrary generator. So my condition is that this G is such that it produces Fk and Gk such that if I change my coordinates and momenta in this way, my Hamiltonian remains unaffected. Not every arbitrary GQP will do that. Right. So there would be a very special form of G which might do that, and my Hamiltonian will commute with those.
Okay, so we are just interested means for those generators which
Yes.
will give the change in S0.
Yes. So those are my symmetries. So symmetries are the basis of, let's say, higher standard physics. Okay. So I'm just basically trying to get you used to um, how to extract physics from symmetry arguments. So uh, if you one day if you calculate in quantum mechanics commutator of something with something is equals to 0, your calculation doesn't end there. You should not be happy just because you have found that. Try to figure out a meaning out of that. I mean, what does it mean if the Hamiltonian commutes with a complicated thing? Then what does that complicated thing mean? Okay. Here it is simple. It's momentum. I gave you this thing. So you all know that p square by twice m commutes with p. You are all happy about that. You did this calculation in quantum mechanics, but perhaps this is one of the, for many of you it is the first time that you try to understand what that commutation basically means. Okay. So your lessons of quantum mechanics doesn't stop at calculating commutator. It's basically interpreting those things and then applying it somewhere else where, say, certain problems have not been solved yet. Okay. So look through the glasses of symmetry, because the symmetry arguments are more general than your this trivial calculation of commutator.
Thank you.
Okay. Anything else? All right. So if not, I will stop recording.